Hey there, this is Math 7, Unit 2, Lesson 7, Comparing Relationships with Tables. So we're going to be looking at a variety of relationships and how they work together, maybe with things like scale factors and rates and stuff like that, but in a table format, so like so. So here we go. Number one, first thing you did in class today was adjusting a recipe, and it said that a recipe calls for the juice of 5 lemons, 2 cups of water, and 2 tablespoons of honey. Or if you were to have that in a chart, you might have a table, you might have something like label, lemon, water, and honey. Is kind of how this one is set up like that. And we had 5 lemons, 2 cups of water, and 2 tablespoons of honey. So that's what our initial table would look like. If we were going to create 4 new versions of that, and we had one that had more lemonade, so the overall we're making, but tastes the same as the original, if we're going to have the same exact formula and have more of it, we could do something like a scale factor of 2, which would mean I take each of those values, 5, 2, and 2, and multiply them by the scale factor to come up with a greater amount of the lemonade, which would be 10, 4, and 4. You could pick any scale factor you want. As long as you apply that through every one of the ingredients, you're going to have the same great taste and just more of it. If I wanted to make less lemonade but the same taste, then I would use a scale factor that would be less than 1. So I could use something like a half, right? I can cut everything in half. So if that's the case, I take my 5, my 2, and my 2, and I multiply them by a half, multiply them by a half, multiply them by a half. I know it's not set up as nice as we might want to see it, but 5 times a half, or 5 over 2, becomes 2.5. 2 times a half, and here it is right here, 2 times a half becomes 2 over 2, which is 1, and that one is 1 as well. So my formula to make the same tasting lemonade, but less of it, could be something like 2.5 to 1 to 1. If I wanted to have a stronger lemon taste, then that's going to mean I need to increase the amount of lemons that I'm using. That number needs to go up. And you can pick any number that you wanted to. So we initially had 5, 2, and 2. I could pick 8 lemons for 2 cups of water, 2 tablespoons of honey. Okay, as long as this number is increasing and greater than 5, then you're going to be okay. If I want to add a weaker lemon taste, now I want to take the lemon value down. So I want a value that's less than 5. So I could say 3 lemons and 2 and 2. Again, as long as that is less, you're in the right ballpark. The next activity was about visiting the state park. And it was talking about going to a park and how much it costs per vehicle and per person in the vehicle. And you used a little problem here that said, okay, it costs $6 per vehicle. There's my cute little vehicle there. And every person inside the vehicle is going to cost $2. Okay? So this is going to be something that every car pays for, but every time you add a person, you're adding $2 more to your bill. But at the same time, that means that it's going to be decreasing the overall cost per person. Let's take a look at this. It says, how much would it cost for a car with 2 people to enter the park, 4 people, 10 people? Record your answers. So first of all, let's keep in mind that the rate per person, right, is times 2. So every person that comes is going to cost $2. $2, $2. So that's going to be how much my person cost will be, is that times 2. But every person is driving a car, so I'm also going to add the $6 vehicle fee to each one of those situations. So 2 times 2 is $4. That's the price for the people, plus the $6 for the car gives me 10. 4 times 2, because 4 people times $2 a ticket is 8, plus the car gives me 14. And then 10 people times $2 a ticket gives me 20, plus the car gives me 26. All right? So for each row in the table, if each person in the vehicle splits the interest cost equally, how much will each person pay? So the idea here is, well, if I take the 10 and I divide it by the number of people, 2, divide it by the number of people, 4, divide it by the number of people, 10, right? I do this, then I end up with 5, I end up with $3.50, this is money, so I can put it in money terms, I end up with $2.60. What we can see is that these values are not the same, right? These are all different values, 5, 350, 260. I can see that the more people I add, 10, the less per person someone has to pay. Okay? So I fill my car with a zillion people, it's going to cost less per person. How might you determine the interest cost for a bus with 50 people? If you were going to do 50 people, you would take your number of people, 50. We would multiply that by the $2 fee. We would add the $6 price for the car, and that would give you your cost. In this case here, 50 times 2 is 100 plus 6 is 106. Okay? 106 people are fitting inside of that car. And just for kicks, if you got 50 people in that car, and you divided that price, now it's going to cost a total of $2.12 for you all to go if you were to take the price and divide it up evenly. Okay? So that would be a division part. So that's just like an extra, you don't have to worry about that. Is the relationship between the number of people and the total interest cost a proportional relationship? Explain how you know. And again, it's something you talked about in class. We would say no, it's not. And the reason it's not is when you look here, these kind of x over y values dividing 10 over 2 does not give you that same rate, the same proportion. There's not a constant proportionality there. And the reason for that is that while this part is staying constant, because we have this vehicle fee of 6, it throws everything off. Because that's actually the value that's being reduced every time you add a person in the overall thing. Okay. What equation could you use to find the total entrance costs for a vehicle with any number of people? So we're talking about if I have people, okay, if I have some people, we don't know, call them P, I'm going to multiply the number of people by $2, right, so $2. I'm going to add the $6 vehicle cost, and that would be my total cost, the total entrance cost. So something like that. So you could have P times 2 plus 6 equals C, or I could write this the other way and say it's C equals 2P plus 6. These are the same things, just written opposite way, depends on which way you want to read that problem out. Okay. The next activity did was on running laps, and it says that two kids, Han and Claire, are running laps around the track. The coach recorded their times at the ends of laps 2, 4, 6, and 8. Okay, 2, 4, 6, and 8, and then we want to complete the chart here. The first question says, is Han running at a constant pace? Is Claire? How do you know? Well, let's find out their minutes per lap, or in a sense, their constant proportionality. To do that, we can take the second value, if we have x, y, and we divide by the first, so 4 over 2 is the same as 2. 9 over 4 is the same as 2 and 1/4. All right, I could write 2 and 1/4, or I could write 2.25. That's fine as well. 15 over 6 is the same as 2 1/2 when I reduce that, so 2.5. And then 23 over 8, it reduces to 3 5/6 there. Okay? When I look at Claire, for Claire's information, we have a 5 over 2, which is 2 1/2. We have a 10 over 4, which is 2 1/2. We have 15 over 6, which is 2 1/2. And we have 20 over 8, which is also 2 1/2. So, is he running at a constant pace? We would probably say for Han, nope, it's not. And the reason is that our constant proportionality is changing every time he's being measured, whether it be 2 minutes or up to 3 and a bit more minutes per lap. Is Claire's pace a constant? Her pace looks like a constant, but we could probably say it's a maybe, it's kind of a most likely. And the reason for that is that while this stays the same, 2.5 or 2 1/2, that's the same. That's also what her time is when she completes that lap. She's gone around one time, and then she's gone around a second time. And we know that by the time she gets here, it's definitely taking 2 1/2 minutes to get from there to there. Okay, we can say that's for sure. We know that. But maybe the way she's running is that sometimes she'll take a lap and she'll sprint the whole thing, and then when she gets here, she just kind of walks out the rest and goes slow. Maybe then after she walks slow, she starts off the next one slow, and then goes, oh, I better hurry up, and then she speeds up. So without watching her run, we don't know for sure, but most likely we could say it seems to be, based upon the table information, a constant rate, but it's hard to verify that unless we're watching Claire run. Write an equation for the relationship between distance and time for anyone who is running at a constant pace. All right, so to do this, we would look at our x and our y values, and so we have the formula we've used before is the y equals the constant proportionality times the x value. And in our case here, we could say y is our time, so we can say time equals our rate. So in this case here, we could say for her it was 2.5, and that would be times the distance. Okay, so we could say t equals 2.5 d, and that's one way we can look at that there. Okay, can you write it a different way? Sure you can. You can write it a different way because we've always said that there are reciprocal k values of constant proportionality. So if we used to have like a 2, we would say the reciprocal of that is 1 over 2. So in this case here, because my constant proportionality is 5 over 2, I could also write that as a 2 over 5 value, but I have to change my variables around just a bit. Okay, if I did the 2 over 5, if you did this one here, that would be going distance, right? Distance over time. So if I'm doing distance over time, if that was something else I was going to look at, if I did distance over time as my 2 over 5, then the number I want to put here is going to be the time, so that the time terms here cancel out, and I'm left with just the distance for my solution. So I could have another one where d equals 2 over 5t. That could also be a solution because it is reciprocal, right? But just depends on how you're looking at it. For what we have here in our x and y table, we would set it up this way with t equals 2.5 or t equals 5 over 2d. All right, so that's how you can end up 2 ways. So this is a little bit of the tricky part when you look at this stuff, because it does matter how you set things up, and it does matter which terms you're trying to eliminate here in this section with that constant. Let's take a look at the summary. So for a summary, we would say that they give you two examples here of smoothie shop, and what you see is that in terms of the dollars per ounce, as our x, our y, and our k, this seems to stay a constant no matter what size smoothie you're getting. Or over here, with our x and our y and our k value, the dollars per ounce seems to change, doesn't it? So you can get a kind of a greater value the larger your smoothie is going to be. And so when we look at that, we just need to say that in these situations, there could be a proportional relationship between the smoothie size and the price. That's what you're talking about there. If there's a proportional relationship, then you can define that as, in this case here, 0.75, which is what we see in this place here. In general, two quantities in proportional relationships will always have the same quotient. That's that y over x value, that quotient there. And then if we know the relationship can be represented by an equation is in the form y equals kx, then we're sure it's proportional. So if you can write that down in a way that shows that it is in the y equals kx formula like this, then we can say that it is proportional. Let's take a look at tonight's homework. So make sure you pause and start back up once you've completed it. Here we go. Decide whether each table could represent a proportional relationship. If the relationship could be proportional, what could the constant proportionality be? So how loud a sound is depending on how far away you are. So we're talking about the sound compared to the distance. Okay, so when we look at the first one, we would take here's our x value or y value, we take our y, I did that last time, we would take our y and we would say 85 over 5. If I do the math on that, 85 over 5 is 17. Okay, that could work so far, but we need to make sure that 17 value shows up in all these other ones when I divide them. So look at the second one. Here's 79 over 10. 79 over 10 is 7.9. Do those two terms equal one another? Nope, they do not. And since they don't, we would say in this case here, this is not proportional, and that's because there is no constant proportionality. You could continue that to prove that to be true, but once we have two values that are out of sync with each other, we really know that it's overall, the whole thing is not proportional. Let's look at the cost of fountain drinks at Hot Dog Hut. Same idea. We're going to take our X and our Y, and we'll take our $1.49 and we'll divide by 16. $1.49 divided by 16 gives you a solution of something like 0.0931, and it keeps going a bit. Okay, so about 9 cents. So it's cost 9 cents per ounce if you get the 16-ounce one. If I bought the 20-ounce drink for $1.59, and I wanted to know what the cost was per ounce there, and I do the math, I end up with 0.0795. So almost 8 cents. We can see that the cost per ounce is decreasing as I go down. And same for the last one. $1.89 divided by 30 gives you 0.063. So I'm getting a better deal as I buy more, but it is not proportional. Okay, and that's because the rate is changing all the way through. So both of these tables are not showing proportional relationships. Let's look at number 2. It says a taxi service charges $1 for the first 1/10 of a mile, and then 10 cents more for every additional 1/10 of a mile after that. Fill in the table with the missing information to determine if this relationship between distance traveled and the price of the trip is a proportional relationship. Okay, so here's what we have. The first guy travels 9/10 of a mile, right? We know that's what's happening. So let's think this through. If it's going to cost you $1 for the first 10th of the mile, let's take our 9/10 and let's break that up. We have 9/10. We're going to use the first 10th of the mile and put that there. And then we know we're going to add an additional 8/10 of a mile for the trip itself, right? That's the first mile, and that's the rest of the trip. The first mile we said is going to cost $1, and the rest of the trip is going to be every 10th of the mile is going to be 10 cents. Okay, so how many tenths do we have here? We have 8, and so 8 times 10 cents is going to be 80 cents. We end up with 1 plus 80 for a total of $1.80 for that trip. Okay, so we're taking our value, we're splitting it up into the 1/10 and whatever's left, multiplying that whatever's left times 0.10 or 10 cents, and then combining those to see what the total cost is. That's just one way of doing it. Are there other ways? There probably are. So this next one we say have a 2, and so 2 is the same as, if I think about it as a fraction, 2 can be written as 20 over 10. 20 over 10, yep, 20 over 10, because if I reduce that, I get 2. I want to put it in tenths so I can play this little game here. So I will have 1/10 is for the starting, the little fee, and then I have 1 plus 19, because 19 plus 1 is 20, and now I have the same type of problem. I know it's going to cost me $1 to start, plus 19 more miles times 0.10, and that becomes a 1 plus 19 times 0.10 is $1.90. So in total, it's going to be $2.90. $2.90. Okay? So that's where we are so far. There are a few more here as we go through, and when you do the work, and I'm going to let you do the work there to solve it, but you should end up with $4 here, and you should end up with $10.90 there. So you need to show your work for this part here, for how you got that. Okay? So do the same idea for this value and that value. For this one, you might want to convert it 10 times 3 is 30 plus 1 and make that 31 over 10 for your starting point, but solve that up there. So the question is the relationship proportional for what's happening? And the reason I would personally say no, it's not, is that while this rate here stays the same, it's a little bit like our problem at the national park we practiced with. Because I have this extra dollar that I'm using at the start, it throws everything off. To be a proportional relationship, we really need to be in that form of y equals kx. I might have a x and a y, and I could maybe find a k value out if it worked, but it's not going to work because when I add that extra thing, that extra plus $1, it throws off the whole thing and it won't work. All right, so I would say no to that one, but you can write that off in your own words. Okay, next we have a race between a turtle and a rabbit. And so we have to look at this chart here and then answer some questions about the turtle and rabbit to decide, are they running in a proportional way? So are either one of these races proportional? Okay, and if so, we can write an equation to show that. So let's take a look first at the turtle. The turtle is running at a rate, okay, here's my x, here's my y. The turtle is running at a rate of 2 over 108 or 1 over 54. Okay, if I made that a decimal, I would have 0.018. For the next one, I have 7.5 over 405, and when I divide that one, I end up with 0.018. 10 over 540 is going to give you 0.018, 18 thousandths. And here we have 32.75 over 1,768.5. You also end up with 18 thousandths. So we can see in terms of my k value, it certainly looks like it would be proportional. Is it going to be for sure? Possibly, and it's more likely sure than not, but we could look at just the chart and say it looks like it probably is going to be proportional. Okay, so what would this formula look like for this? Again, there would be 2, because if I look at this way, if I'm looking at time compared to distance, I would do, if this is the t, right, this is t and this is d, I could look and say it's t is equal to my constant proportionality 1 over 5/4 times the d value. That's one way of looking at it. If I wanted to change those around and go the other way, I could say that the distance is going to be equal to 54 times the t of the time value. So both of those actually work in terms of how you would set that proportion up. Depends on which way you're looking at it. If we're going x, y, and k, it lands that way. If we wanted to change the columns around, it would go this way. Looking at the rabbit's run, you would do the same idea, 1 divided by 800, and that's going to give you 0.00125. When you do 5 divided by 900, you get 0.0055, and already you can see these are going to be different values all the way down, and so we would say that it is not proportional. Okay, because they're different values all the way down. The rabbit was running at a crazy rate. That's probably why he is a rabbit. All right, and number 4, for each table, answer what is the constant in proportionality. So to find that k value, we divide, right? To find the k value, we're going to divide b over a in this case. That's our x and our y. So 14 over 2 equals 10. We could double check to make sure that's true all the way down. 35 over 5 is 10. Why did I say 10? 7. 42 divided by 2 is 7. 35 divided by 5 is 7. 63 divided by 9 is 7. And this one is also 7. So does it have a constant proportionality? Yep, k equals 7 right there. On this next one, we do 360 divided by 3, which equals 120. And then you have 600 divided by 5, which equals 120. Is it a constant proportionality? Sure is. It already told us it was. It's going to be k equals 120. You don't have to do all of them. It's just asking you what is the constant proportionality, which is kind of a clue that says there is a relationship between the two terms, so just find it. So maybe find the easiest one to do. So on this one here, if I'm doing 0.4 divided by 10, okay, then maybe I go, oh, I could do that. That's going to be, you know, a tenth of that. whatever you want to look at. This is 3 over 75, which becomes 1 over 25. Okay, that's my k value, 1/25. And over here, I have 10 over 4, which becomes 5 over 2. So my k value can be 5 over 2, or I could write it down as 2.5, whichever way you want. Okay, the last one here, it says that Kieran and May are standing at one corner of a rectangular field. So let's pretend this is the rectangular field, and they're standing here having a great time at the corner of the field. And they're rectangular field of grass looking diagonally at the opposite corners. They're looking from here over to there. Okay, great. Kieran says that the field were twice as long, so let's go twice as long, and twice as wide. So let's make it twice as wide. Then it would be twice the distance to the far corner, to be over here, twice the distance. May says that it'd be more than twice as far since the diagonal is even longer than the side lengths. Do you agree with either of them? Okay, so this is really a question about scaling. When we scale something, remember, angle measurements don't change, but if this length, let's say it was a 1, okay, and let's say, well, let's go with 2. Let's pretend this was 2 and this was 1. Let's just pretend there for now. If we doubled it and this became 1, then the overall becomes 2, correct? And if we doubled this and that was 2, the overall becomes 4. Our other length here, I'm not sure what it would be, but let's just call it x. That length there, if it's doubling to go here, is also an x, and it becomes x plus x, 2x. So is it twice as long? It certainly is twice as long, because when we do scaling, the length of the diagonal is also going to be multiplied by 2, become twice as long as well. And you can see visually there that, yep, it does work out. Hope that helps with your homework. Have a great day, and we'll see you next time.